Good. Good morning, everybody. Welcome to another wonderful day in fluids. Today, we're going to discuss hydrostatics of liquids and gases, as well as a brief discussion on some introductory fluid mechanic principles in terms of how we define and describe fluids in order to make reasonable approximations for engineering calculations. So I'm going to flip it over to the whiteboard. And here we're going to start jumping into some of our discussion material. So let's say today we're going to be looking at our introduction to fluid mechanics. And fluid statics. So first, we can't have a fluid mechanics discussion without first defining what a fluid is. So can someone give me their best definition for how you would define a fluid?
A substance that is a solid, liquid, or gas.
Close. I wouldn't call it a solid a fluid. You can say liquid or gas. That is categories. Anybody else have any other ideas?
Just more generally, is it like a substance that doesn't have shape necessarily?
Yes and no.
Okay.
That's part of it. You are on the right track.
Would it be a substance that deforms under shear stress?
Yes. That is the most, I would say that's the scientific definition, is a substance that continuously deforms when subject to a shear stress. The engineering definition, I would say, is liquids, vapors, and gases. So with this crude definition of fluids, while helpful, it doesn't really give us a whole lot to go off of when looking at engineering systems and performing engineering calculations. And so we often like to differentiate fluids into various categories based on what we can expect from their physical and chemical properties. So I'll just say we like to differentiate between fluids based on certain physical and chemical properties. And we can spend all morning talking about the various classifications, but we're going to touch base on a few. The first one being fluid density and how it relates to what we call fluid compressibility. And from this, we categorize fluids into one of two categories. We can consider a fluid incompressible, or we can consider a fluid a compressible Yeah, my pen gets a little shaky, sorry. So how do we suppose we categorize fluids? And what do I mean when I say a fluid is incompressible versus compressible? What are your thoughts? Anyone want to take a guess? I need to get the like Jeopardy noise in the background. There are no wrong answers. Only silence is the wrong answer.
Oh,
Okay, for a compressible fluid, an increase in pressure will increase.
Okay, so you said for a compressible fluid, increasing the pressure increases the density. That is correct. Is it only pressure that influences what we consider compressible? Do you think yes or no?
No.
What other characteristic might be in that category? What we can call the salt and pepper of chemical engineering.
would it be heat?
Close, it would be temperature. So technically, yes. So for a compressible fluid, I would expect significant changes in fluid density. I need to get a better pen. Density with respect to temperature and pressure. Yeah, I call those the salt and pepper of chemie. If you don't know what to do, look at the temperature and pressure. And then for an incompressible fluid, I would expect negligible change. In fluid density with respect to fluid temperature and pressure. So when we think of an incompressible fluid, more often than not, we're really talking about liquids. And when we're looking at compressible fluids, we're really a lot of times talking about vapors and gases. Now, that's not going to hold in every sense, primarily because when you're looking at large changes in temperature and pressure, there will be density fluctuations for a liquid. However, in general, beyond those regions, we can largely consider liquids incompressible fluids, and compressible fluids will be mainly vapors and gases. And at the same time, like if your delta P is small or your delta T is really small for a gas, there are instances where we consider them to be incompressible for the purpose of making calculations much simpler. Is everyone with me on that discussion? Yes? All right. So let's consider the implications of compressibility when we're looking at this example. An example that's going to happen, I don't know, at least a dozen times in this class. Flow through a pipe. Where we have flow coming in on the left, it's leaving on the right. And let's say I'm going to say I have some pressure that I don't know, P1 on the left, some pressure P2 on the right as it leaves this pipe. And my question is, what happens to these pressures as a fluid moves through the pipe. Meaning, let's say if I have P1 greater than P2, is P1 equal to P2, or is P1 less than P2? What do you guys think? And let's play, we could play my favorite game, rock, paper, scissors. So, based on these three choices, if you think that P1's going to be greater than P2, choose rock. If you think the pressures are going to be equal, choose paper. And if you think P1's going to be less than P2, you can choose scissors. So what do you think? I'll give you guys 5 seconds. You gotta get it ready. If you have the camera on, if you don't have the camera on, you can always, do the old chat. You guys ready? I know you guys are gonna have to participate. It's game time. Ready? Rock, paper, scissors, shoot. All right. I got some rocks, some politically correct papers. Not seeing a whole lot of scissors. All right. The answer is rock, and that the pressure going into the pipe will be higher leaving the pipe. And the short answer is because of shear stress. The longer answer is something we'll get into here in about a week or so. So pressure falls, decreases through the pipe. My follow-up then is, what are the implications for incompressible fluids and compressible fluids? Due to the decrease in pressure. So looking back at that, pressure's falling through the pipe, and let's say I have water, which I can consider incompressible. What's going to happen to the density of water as it moves through the pipe?
It will remain the same.
It's not going to change, right? The density is going to be constant. Rho is constant. And I will give you my caveat disclaimer now. There's going to be a lot of P's and rho's in this class because P is pressure, rho is density, and sometimes it'll be hard to just delineate. So let me know if you get confused. Now, what happens if I have natural gas, which I would consider compressible, flowing through, let's say, a pipeline? What's going to happen to its density?
It will change as it flows through the pipe.
Yeah, so is it going to increase or decrease? What do we think?
I would think it would decrease.
You would be correct. And so as the natural gas flows through this pipeline, its density is going to decrease because the pressure would fall. And there are some significant implications associated with this density variation, which was what makes compressible flow kind of a headache. And we will kind of refer to this illustration at various points in the semester. But just kind of keep that in the back of your mind in terms of compressible flow versus incompressible flow and what that means when you're moving through a system. So let's talk about, switching gears a little bit, one other variable before we start jumping into statics, and that would be fluid viscosity. Now, variations in what we see with fluid flow and viscosity allows us to categorize fluids into one of two categories. For the sake of this class, we would look at things in terms of them being what's known as a Newtonian fluid versus a non-Newtonian fluid. Where a Newtonian fluid would be a fluid that would exhibit a constant viscosity as a function of a velocity gradient with no presence of elasticity. And then a non-Newtonian fluid, simply put, is a fluid that exhibits variable viscosity as a function of a velocity gradient with evidence of elasticity. And I know those definitions are kind of wordy and they really don't explain a lot. So let's look at it this way. When we're looking at a Newtonian fluid, we can describe its behavior in terms of shear stress exerted as a function of both its viscosity as well as the velocity gradient that it's subject to under flow. What that means is if I have flow through a pipe, it's going to exhibit shear as a result of that flow. And the shear we can express is linearly correlated with the gradient. So if I have, let me find that real quick. A graph of flow gradient and shear stress, a Newtonian fluid is going to demonstrate this linear behavior directly tied to having this nice constant viscosity. However, if this behavior in terms of shear versus velocity gradients is nonlinear, we consider anything outside of that trend a non-Newtonian fluid. So this would be Newtonian. Then you can have things that are considered shear thinning or shear thickening, things that lie outside of this curve. You can also have some, which are a few, that there's almost like an activation energy for flow, and then it behaves like a pseudo Newtonian fluid. Now you might have talked about these a little bit in transport. We really don't get into them a whole lot, but what you need to know is that when these fluids don't have a constant viscosity or they demonstrate some form of elasticity, the Newtonian assumptions that we will make in this class will quickly break down. And that means additional corrections for some of the material and energy balances we derive will be necessary. So it's important to keep in mind. I would also keep this equation in mind. We'll probably refer to it in a few derivations further on in the semester. And so simply put, in terms of viscosity, most things that you're going to encounter will be Newtonian, where you can consider they're having a constant viscosity for any given temperature and pressure. When things have a variable viscosity, meaning the viscosity is going to change as a function of that flow, that's when things are going to get more complicated and corrective factors are going to be necessary. All right. Now that we've got through that, one other couple things that I might want to touch base on is a discussion a little bit more on stress. Now, stress is a force divided by an area upon which it acts. We can break this out into two categories, where if we have a normal stress, it acts perpendicular to a force, to the surface at which it acts. And we have shear stress, which acts parallel to the surface upon which it acts. More times than not, when we're talking about normal stress, we refer to this as pressure. And pressure we can describe in terms of what's known as a gauge pressure, or an absolute pressure, where the gauge pressure is a comparison pressure, not considering atmospheric pressure. So I can say PSIG is equal to P minus, it would just be pressure read from a gauge. The absolute pressure, or if I'm looking at PSI, PSIA, it would simply be the PSIG plus the atmospheric pressure. Now, in this class, oftentimes we're going to be looking at a gauge pressure because it allows us to dramatically simplify our calculations, particularly as it relates to our energy balances. And so it's important to note when you're doing engineering calculations, whether you're looking at things in terms of a gauge pressure or an absolute pressure, and just make it apparent as you're doing those calculations. I don't think it's in this one actually, hold on. Also, one thing I like to bring up, since we get on the subject, is essentially how a pressure gauge works. So how many of you have have had the wonderful opportunity to investigate how pressure gauges work and the mechanisms on which they act. Nobody? Okay, that tells me that everybody's Netflix account's working today. So I think it's an important thing for us to consider as engineers, primarily because if you're going to be looking at metering and measuring devices, understanding the mechanisms upon which they work is an important way to troubleshoot their operation, as well as to get a better grasp on the principles. So if I'm looking at a pressure gauge, you know, a lot of times I've got an arrow. Let's say it's in, you know, PSI. Here will be 0. And let's say I have 5, 10, 15, 20, 25. Let's say this goes to 25, right? There's going to be ticks. And whatever that points to is going to be what the pressure that it's reading in the gauge. If we take a close look inside of that, what you're going to see is a device that looks like this. And I know everybody loves my artwork. And so you end up with this essentially hook-looking tube that's called a Boredom Tube. And that Boredom Tube connects via a fitting here to whatever fluid that you want to measure the pressure of. That pressure exhibits, or that, excuse me, that fluid exhibits a pressure on essentially the fluid that's within the Boredom Tube. And that pressure gets manipulated at the tip of the Boredom Tube through a couple of linkages to the center, which has a gear and a pin. And as the pressure gets exerted in the tube itself wants to essentially bend outwards. And so the higher the pressure that's within the tube, it will bend itself outward, more towards the edges of the gauge. And that outward movement causes these pins and levers to adjust on the gear. And that is the mechanism upon which the arrow on the actual reading device moves. And so it's this essentially flexing and deflection of this Boredom tube that causes that arrow to move back and forth. Now, I'll probably post on the module page later today a video that describes it in a lot better detail where you can actually see a picture of the Boredom tube. But I think it's an important thing to kind of touch base on. It jumps into a little bit more about the applications and the devices upon which these principles are applied. And so it's something that you always want to keep in mind, you know, how we can use pressure to design the systems that monitor it. So any questions on, you know, what I've discussed this far, looking at what fluids are and how we use their physical properties to lump them into categories? Riveting stuff, I know. I appreciate everyone's attention. All right, so now let's jump a little bit into fluid statics, also known as hydrostatics. So if I had a column of fluid, I could say that there's some pressure at the top of that fluid, P1, and some pressure at the bottom of that fluid, P2. And I guess if you want me to be super mathy about it, I can define it as P sub z plus dz, with the height of this calling being a differential height, or a dz. And then I can ask myself, can I determine the difference in the pressure from the top of my slice of fluid to the bottom of my slice of fluid? So what is the pressure difference? Well, I'm looking for P z plus dz minus P sub z. Well, the difference in that pressure is going to be essentially the force of the fluid, which in this case would be the weight of the fluid over the area upon which it acts. So I can say, well, if I want to do some form of a force type balance, I can say that times area is equal to the weight of the fluid, which is the mass of the fluid times gravity, and if I wanted to break that out, I can say, well, it's delta z minus pz, because it breaks upon area. The mass of the fluid is simply the volume of the fluid, which I'll take V, times the density of that fluid, rho sub F, times gravity. But let's say I wanted to break this out. Well, that's the volume of the fluid. Well, the volume of the fluid is the area of that slice times the height times the density of the fluid times gravity. And so now what I'm left with is the difference in these pressures, getting rid of that area term, is simply the density of a fluid times gravity times the differential height. So if I take that in terms of an integral of 0 to z, I'm left with P z plus delta z minus Pz is equal to rho f g z. Or simply for any given pressure, I look at the reference pressure, P sub naught, plus rho f g z. And this is my fluid statics expression. What that tells me is that my pressure will increases linearly with height. And if I want to express things in gauge pressure, more often than not, I just set my P naught equal to 0, and my pressure that I'm interested in is just simply rho gz or rho gh. So where do we apply this? Well, we'll apply it in many areas, but one way we can talk about this is, once again, in some more pressure measuring devices. And for right now, we're going to look at everybody's favorite, manometers, which are devices used to measure relative pressures based on the height, or I should say the height of reference fluids. And so a good example of this would be if I had a manometer where a fluid happened on this one side. P1 is largely unknown. I could have a second reference fluid that unknown pressure can exert itself upon. And if this was open to the atmosphere, I can identify the delta P, or P1 minus P0, simply as the density of that reference fluid times gravity times the height difference between both sides of this manometer, or rho GH. In terms of the reference fluid, a lot of times historically you've seen mercury used because its specific gravity is so high, 13.6. So it was a really dense fluid. So large fluctuations in pressure would result in very minor changes in height. So you didn't need a large manometer. However, we learned probably shouldn't have mercury hanging around places. And so more often than not, you'll see really dense oils used in its place. More safe oils. Yeah, those chemists back in the day like to live life on the edge. So let's look at an example. All right, everybody see this picture? We got a tank filled with two different liquids. A liquid A on the top and a liquid B on the bottom. Now we see there's two manometers in this drawing, where the manometer coming off A is just going to go right to the top of A, but the manometer coming off the quote-unquote bottom of B doesn't go all the way to the top because it has a different density. And so my question would be, if these manometers were drawn better such that they were at the bottom of those two liquids, what would be the height of the fluid in manometer B? So keeping, the liquid B's from 0 to 0.3 meters, and liquid A is from 0.3 meters to 2 meters. Or liquid A has a specific gravity of 0.72. Liquid B has a specific gravity of 2.36. So let's take a look at this. Going back. One thing I always recommend students do when you're looking at homework problems or doing any sort of calculation is drawing the problem. Even if you don't have the world's best artistry skills, it still helps. So we've got a manometer here, and we've got another manometer here. And just for fun, I'll make liquid A blue, and liquid B can be green. And I'll say A has a specific gravity of 0.7, what was it, 2, and B had the specific gravity of 2.36. So what we're looking for is this one went all the way to the top, this one not so much. So what is this height here? So what's the best way to jump into this problem without actually jumping? And besides Google. Well, one thing we can look at is what's the pressure at the bottom of this tank? Well, the pressure at the bottom of the tank, if this is atmosphere, I can say, well, assuming looking at my gauge pressure, what do you want to call this? P sub B. P sub B is equal to the density of fluid A times gravity times this height here, which I'll call H1, plus the density of fluid B times gravity times the height here, which I can call H2. So PB then equals specific gravity of A, which is 0.72, times the reference fluid, which if you're looking at liquids, reference fluid will be water. If you're looking at gases, reference fluid will be air. And so this is a metrics problem. So the density of water is 1,000 kilograms per cubic meter. The height that we had is 0.3 to 2 or 1.7 meters plus the density of B, which was 2.36 times 1,000 kilograms per cubic meter times 0.3 meters, which, if we do all that fun math,
Dr. Lucas,
yes.
did you forget the gravity term or?
Oh yeah, I did. Thanks. I said I knew this number seemed small. 9.81 meters per second squared. Let's see, this was 2.36 times 1,000 kilograms per cubic meter, 0.3 meters, and 9.81 meters per second squared. Which gives you can double check my math if you'd like, no shame in that. About 8.2 kilopascals, or 8,169 pascals. The good thing about doing things in SI units is you don't have to worry about doing any crazy conversions because it all just kind of goes into pascals. So then the question is, well, what's the height for this top of the manometer? Well, if these manometers are both open to the atmosphere, then we have to have the same pressure difference over the height of the fluid in that column. Meaning the row of the fluid there times gravity times the unknown height, which we'll just call h by itself, has to equal PB minus P atmosphere, since we're using gauge, is just this 8.2 kilopascals. So knowing that, we can solve for the height by saying 8,169 pascals divided by 2.36 divided by 1,000 kilograms per cubic meter divided by 9.81 meters per second squared. We do that, we should arrive at the height of the fluid in that second manometer. Which I got about 0.35 meters. Any questions on this example in terms of application of fluid statics to look at manometers to calculate relative height differences?
Dr. Lopez, when I was calculating the pressure at the bottom, I calculated 18,952. And I did the math twice for that one.
I'd be happy to check mine.
Okay.
I'm just using a phone calculator here, so I'm probably liable to make. Your 18,000 makes a lot more sense, I'm not gonna lie.
I think I figure out where you were wrong. You forgot to multiply the row A, or the liquid A by 9.81, but you remembered
9.81.
it with the second one.
That makes sense. So I apologize for that. Yeah, 18.95 kilopascal makes a lot more sense. The approach is the same. Let me just update my solution then. Which means you're gonna have much higher off of the manometer. About 0.82 meters. Okay, well, thank you for that. All right, any questions on that? Okay, let's look at one more example. Now I have an oil tanker that has a manometer coming off the side, and I want to know what's the pressure at point A in PSI if I've got a manometer filled with mercury, because I like to live life on the edge, and the mercury has a specific gravity of 13.6. So I'll give you guys a quick second to make note of this one. Okay, let's jump back in and see if we can work on this one together. Now, probably should make sure you can see my screen. We got a point A here, manometer that looks like this. What do we want to fill this with? You guys have any color preferences? That looks fancy. Mercury. S equals 13.6. This delta H, I believe, was 1 foot. And then the delta H here for this fluid was 7.22 feet. And this was open to the atmosphere. So once again, we're going to look at gauge pressure. And looking for the pressure at point A. So the best thing to look at is calculating the pressure differential here to get an idea of what's going to be the pressure around the mercury to get to the pressure at A. We do that. That first pressure differential, delta P1, is going to be the density of mercury times gravity times 1 foot, where the density of mercury, specific gravity, is 13.6. The density is, once again, we're using the reference of water, but since we have feet involved, we're going to be looking at English units, and the density of water in English units is 62.4 pound mass per cubic feet. Gravity is 32.2 feet per second squared. And so when we do this calculation, we're left with 27,326 pound mass. Oh, I forgot the 1 foot, excuse me. Per foot second squared. And so right off the bat, you'll realize that this doesn't really tell us a whole lot in terms of the units. And so what we're going to have to do is divide by the gravitational constant G sub C, 32.2 pound mass foot per pound force second squared, and then convert our feet squared into inches squared. What we would be left with, when we take a look here at the canceling of the units, is pound force per inches squared, or simply PSI. And it's PSIG because we're looking at it in terms of gauge pressure. So we end up with 5.89 PSIG. And that's the pressure here in the system. And so to find the pressure at A, we have to subtract the pressure associated with the height of the oil that we see on the left-hand side of the manometer. So PA is going to be this delta P1 minus the density of the oil times gravity times the 7.22 feet. So PA is going to be 5.89 PSIG minus the density of the oil, the specific gravity, if I remember correctly, was 0.91 times 62.4 pound mass per cubic feet times 32.2 feet per second squared times the 7.22 feet. Once again, we'll have to divide by G sub C, 32.2 pound mass foot per pound force second squared. And then once again, 1 foot squared is 144 square inches. We do all that, we should be left with about 3.05 psi G.
I have a question.
Yes.
Would you explain why we didn't take the delta H? I was thinking, since it's a change in height of fluid, we would use 6.22 feet instead of 7.2 feet.
That's a good question. The problem with that is you have to consider the pressure implications of the mercury. And so this change is due to mercury with this specific gravity. And so if you just do the 6.22, you're not keeping in mind the differences that are present due to the two different fluids, right? Because this oil is pressing on the mercury with a certain amount of pressure, but that pressure only causes a small deflection in the mercury. And this is a large reason of why mercury was popular for manometers, because it was reliable and you can have large pressure changes evidenced by small height changes, right? Because if that was water, that,
A lot
you know,
higher.
the difference between those two sides is going to be 13.6 feet, which is drastically different than just 1 foot in terms of the design of that manometer. I don't know about you, but I don't want to read a 14-foot manometer.
Okay, thank you.
Of course. Any other questions or things and points of clarification? All right, so now we've been looking at this fluid statics as it applies to mainly incompressible fluids, right? And we came up with an expression, P is equal to P naught plus rho GH. So what happens when we consider compressible fluids? What's going to change in our expression?
Rho is no longer constant.
Rho is no longer constant, right? So the density will change. And so we can't use the expression as it's written here. We need to figure out how density is going to change as a function of pressure fluctuations. So what do you suppose we can rely on to get a good estimate for density fluctuations due to pressure?
Could we look at pressure change?
Well, if we go to the ideal gas law, PV is equal to nRT, I can come up with an expression for density as a function of pressure. Simply because the number of moles is my mass over my molecular weight, right? So I can rewrite this as PV is equal to mRT over mW. And density is just mass over volume. So with these two things in mind, I can then say mass over volume, which is density, is equal to P, molecular weight, over RT. So plugging that in my fluid statics expression, I end up with pressure is equal to P naught plus PMW over RT GH, which, while helpful, isn't the full story. Primarily because if I rewrite things in terms of gauge, right, I can say P is equal to PMW over RT GH. Which, kind of helpful, still not the full story. But what I can do then is revisit that same P naught differential height. But now instead of looking at a liquid, now this is going to be a gas. And then I can say, well, what's going to be that influence of pressure as a function of height? Well, it should be PMW G over RT, where if I rearrange that to, separate the variables, separation of variables, I'm left with delta P over P is equal to MWG RT DH, which I'll have to integrate this from P naught to P, and then I integrate this from 0 to H. Or if you want, I can use Z's, be more consistent. I'm sorry if I know you going for C's and H's. I'm just going to leave it with H. If I integrate and solve, I'm left with P is equal to P naught, the exponential of negative molecular weight G over RT times H, which is a reasonably important equation, which we call the barometric equation, which describes fluid statics as it applies to compressible fluids. And so by inputting the pressure or the density correction using the ideal gas law, we can redefine our fluid statics expression. However, it results in looking at that original derivation, we have to tweak it because this pressure is in the denominator. And since it sits there in the denominator, we end up with this new expression with our exponential term. Is that clear as mud? Are there any questions? So let's look at an example of applying the barometric expression. So let's say if you visit Denver, it has an elevation of 5,280 feet, known as the Mile High City. What is the absolute pressure of a home in Denver? Keeping in mind this expression The molecular weight of air is 29 buckets per bucket mole. Really doesn't matter what unit you want to use. The temperature, let's say it's a nice day, 60 degrees Fahrenheit, which I don't know what that is in Celsius off the top of my head. Probably 19 or something like that. Oh, 15.6. I would probably use for R 0.08205 liter atmospheres per mole Kelvin. And like I said, the height was 5,280 feet, which in meters, because I don't want to be too mean to you all, about 1,610 meters. So I'm going to give you guys like 2 minutes to work on it, see what you can come up with. Actually, if you want, I'll try something new. I'll send you guys into breakouts and y'all can work in groups of 3 and 4. I'll give y'all 2 minutes, okay? And then you'll come back. So work together. You can join a random group room if you would like, Elahe. Actually, hold on. I need to find a way so it doesn't include you in this. How's it going, Carl and Anna?
Doing good. How are you?
Doing all right. I realized that only for some reason made this a 2-person room. I figured I'd come in and see what I can do to help you all.
This is interesting. I kind of like it.
Oh, the shooting you all into rooms to talk with a couple of you? So what do you think would be the best step to get started on this problem?
Probably just start plugging in what we've got, making sure all the units all line up into the barometric equation.
All right. So let me know. I'll give you guys a minute or 2 to do that. Let me know what you come up with.
Perfect.
How's it going, Elahe?
I'm good, Dr. Lopez. Just struggling, trying to get graduated.
All right. Let everybody come back, and then we'll go ahead and talk about the solution and what everybody got. So did any group get an answer?
I have a question.
Yes, of course.
What is P naught?
P naught would be the reference pressure. So in this case, it would just be atmospheric. So 1 atmosphere or 14.7 psi.
Okay, thank you.
Of course. But all good questions. So did any group get a solution? Yes or no? No? Okay, let's take a look at it as a group then. And then we'll. So one thing that it's important to note when looking at the barometric expression is that the units of pressure in P naught, P and P naught, are going to be the same. That means everything in the exponential has to cancel, right? Because with exponentials and logs, everything, you can't have units go through those calculations. So your molecular weight times gravity over RT times H, all the units have to cancel. So if I want to do this in SI units, what I can do is the following. Well, with the molecular weight being 29 kilograms per kilomole, there's 1,000 moles in a kilomole. My gravity is going to be 9.81 meters per second squared. For R, I'm going to use 8.314 joules per mole Kelvin because that's the most convenient thing to use for SI units. And then for my temperature, I have to use absolute temperature. It's in Kelvin. And when I'm doing these types of calculations, that absolute temperature is going to be very important. So I use that with Kelvin, the moles cancel, and then I have my meters. And then I have kilograms, meters squared per second squared, which is a joule. And so I'm left with a unitless value. So if I do that, and I run that calculation, what you should be left with is that your exponential you're left with is, oh, wrong pen, excuse me, P is going to be equal to P naught times 0.83, which means the pressure, or the absolute pressure in Denver, is going to be about 0.83 atmospheres or 12.2 psi-A. Any questions on that? So go ahead. I would recommend, we're out of time, but in the lecture notes and slides, there is a second follow-up about traveling to Pikes Peak. Go ahead and do that one and double check your answer. With that one, you should get a much lower pressure of about 0.61 atmosphere for Pikes Peak. So go ahead and do that one in your spare time. Make sure you can run the calculation yourself. And if you have questions, feel free to reach out. Thank you guys all once again for attending today's lecture. Don't forget, your first homework assignments are going to be due tomorrow, with the quiz being due on Sunday night. I will release the second module later this afternoon. I'll send you an email once that's available. That will be getting more into the mass and energy balances associated with fluids. Any last minute burning questions? If not, I'll let you all go to have a great class. I know seniors, you all probably having to run the design maybe. But if not, take care and have a great rest of your day.
Thank you.
Thank you.
Thank
Bye,
you.
Dr. Lopez.
Have a good day, Dr. Lopez.
You too. Have a great day.